Dear audience, topic of my presentation is flow condition of new turbulence promoter geometry optimized for membrane filtration. There are several fields in food industry where filtration process can be intensified using turbulence promoters inside tubular membrane. And in our earlier research we proved that using of Kenix type static mixer it may have a positive effect to the permanent flux and to the retention. Kenix static mixer is designed for fluid mixing, not for membrane filtration. And it has a big disadvantage that if we put a Kenix static mixer inside the tubular membrane, on higher flow rates it will cause higher friction pressure drop along the membrane. So it can be used only on lower flow rates. And on the basis of these results, we have studied new geometric configurations where our aim is to find a turbulence promoter which will keep the advantage of the Kenix static mixer, but it will not cause the higher pressure drop along the membrane. The work was started with design and analyzing of new forms with help of computational fluid dynamic simulation, the CFD. The input in the CFD is the 3D matrix where the space around the membrane was divided into particles, and 0 is, for example, where the fluid is presented, and 1 where it not fluid. And also with the starting parameters, this is the input, the CFD calculate the position after 5 or 10 seconds, and the result, the output is also the 3D matrix, which can be, for example, visualized using ParaView. It is very popular open source software for these purposes. Just a few words more about the CFD. We used a lattice Boltzmann algorithm. We calculate for each particle the Colson spread and calculate the macroscopic quantities, the density, velocity and vorticity. Of course, for fluid the density is constant, so we need velocity and vorticity from this. And the result, as I mentioned, is 3D matrix which visually looks, for example, like this. Here you can see vectors, for example, for particles, or it can be visual with different colors, or, for example, the flow path lines can be seen here. But as you can see on this scale, there are numbers, values without units, so we don't know what is the unit for this. To get some useful information from this, we have to compare some results. So, for example, here you can see the result of the CFD for Kenix static mixer, and it is compared with 5 new geometrical shapes. For example, if we take that this is 100% of vorticity normal, and compare the other 5 static mixers, we will get this equation. So even on the 50 liter per hour, which is low flow rate simulated, we get much better results, smaller vorticity normals for new turbulence promoters. And these 5 new turbulence promoters were produced and tested under real conditions. For example, I tested with the whey and oil in water emulsion. Here I will show you the results of the oil in water emulsion separation. There is, in function of flow rate, the retention. You can see that every static mixer improved the retention of the oil. With the red, there is the empty tube membrane without mixer. On next graph, there is initial flux in function of the flow rate. Of course, the lower is the empty tube membrane without static mixer, and the best result we get with the Kenix, and with the number 3, let's call it spiral static mixer. And the third, in functional flow rates, the pressure drop along the membrane. So this is why we were searching for new geometric shapes. You can see almost every new static mixers, and of course the empty tube have lowest effect to the pressure drop along the membrane, and the Kenix static mixers, especially on higher flow rates, have much bigger friction in our case. So out of 5 new static mixers, turbulence promoter with most optimal geometry was the spiral static mixer with trade pitch and diameter ratio of 2. Pitch angle was 32 degrees and twisted metal strip thickness approximately 1 millimeter. So this can be seen here on this picture. And here you can see the specific energy consumption. So when we started, we know that Kenix static mixer can be used only on lower flow rates. On higher flow rates, it have very big specific energy consumption, but new spiral static mixer, even on higher flow rates, have lower specific energy consumption. Reynolds number. For commercially available static mixer, usually manufacturer provide equation for calculation of the Reynolds number and the pressure drop along the membrane. Just for example, here I will show you the FMX type static mixers technical introduction. So here we have some user-friendly equation where we can calculate these two numbers. Since this is spiral static mixer is new product, these equations has to be developed. The Reynolds number can be easily calculated with the existing equations. Where this equation, the inner diameter of the pipe multiplied by velocity multiplied by density and divided with the dynamic viscosity, but it is for empty tube. Since we have a static mixer installed here and the pad is not linear but spiralic, we have to modify these two numbers. We have to calculate the hydraulic diameter of the pipe and the mean velocity of the fluid in tube with static mixer. Hydraulic diameter of the pipe can be calculated with the existing equation. So 4 multiplied by cross-sectional area divided by wetted perimeter. I don't want to go into the details too much, so at the end you can see the relationship between hydraulic diameter of the pipe and the inner diameter of the tube. This will be used later in the equation. And mean velocity of the fluid in tube with static mixer. This would be the speed, reciprocal flow rate divided by cross-section area would be if the path would be linear, but it's not linear because we have a flow angle here which can be calculated from this triangle or from the trade pitch angle, and we will get actually the real velocity of the particles in the membrane. And this equation can be placed in the Reynolds number calculation. This is the final result, but in this form it can be used only if the variables are in SE units. To get more user-friendly equations, I modified it a little bit where the flow rate is in liter per hour, which is more commonly used unit, and the diameter is in millimeters. And we get this equation for calculation of the Reynolds number. And the pressure drop along the membrane. Equation for pressure drop along the membrane has to be created, but we cannot use the existing equations, for example, Darcy-Weisbach equation, because we have two unknown variables inside. We don't know the friction factor or flow coefficient between fluid and membrane, or fluid and material of the static mixer, and we have two different materials here. And also we don't know the equivalent pipe length also, because here we have installed static mixer. So this equation for prediction of the pressure drop along membrane can be developed based on experimental results. So this is in practice, it's not finished here. Conclusions: new turbulence promoter was developed and tested, and this new spiralic static mixer keep the positive effect of the kinestatic mixers, the initial flux rate and retention, and also it doesn't result high pressure drop along the membrane. Even on higher flow rates, this means the falling of the membrane will be more delayed. And specific Reynolds number formula was established for sizing calculations. In my experiments, I was working only with two materials, with oil in water emulsion and with whey. But new static mixers has to be tested with much more materials. And on our department, my colleagues already started with using of this new static mixer. So, for example, they are using already emulsification, fermentation, juices lapping, filtering of beer, whey and milk filtration. Thank you for your attention.
Now I ask the audience whether you have some questions.
This is turbulence promoters, the new ones that you tried. Are they already available, or did you develop the size and the diameters of those promoters?
Well, it was developed with cooperation with the university in Novi Sad. It was a company in Serbia who produced these new static mixers, tested the 5 new static mixers for us, but only for us. They are not available in
so this is also
production.
part of the development.
Yes, that's right. That's right.
Thank you very much.
Thank you.
And we move to the second